Imagine if I'm given a data matrix X where each of my rows F1, F2, sorry, each of my columns F5, so on and so forth is a feature, and each of my points X1, X2, so on and so forth, Xn, Xi here and Fj here. Okay, so and my data point here is Xi transpose. Okay, so this is an n cross d matrix. I'm sorry, I have tilted this line, I've slanted this line too much, but you get the gist of it, right? So let me just correct it. Okay, so you get the gist of it. So if this is my data matrix, I'm not even looking at y, right? But let's just write y here. So here is my yi, okay, corresponding to my xi. Now where yi is a n cross 1 column vector, right? These are my class labels. Just what we saw a while ago. So there is something called data pre-processing. Okay, this is how my data set is given to me. Okay, so now data pre-processing. The word pre-processing basically refers to some type of mathematical operations and transformations that we have to do on the data itself. Okay, before we go and do other more complex data transformations. For example, we wanted to do dimensional reduction, right? So as to visualize data more efficiently, or even to before we build models, we do the pre-processing. Basically means what type of operations do you perform before you actually go and build models, or before. So typically what happens is you do data pre-processing before as a stage, right? You obtain your data, and then you perform bunch of data pre-processing operations. Okay, depending on the problem, and then you do your modeling, data modeling. That's what I meant. Okay, so as part of data pre-processing, there are multiple operations. One of them is called column normalization. Okay, whether you do column normalization or not, there are many types of data pre-processing. Okay, again, it's very problem specific. We'll learn about some of the most important data pre-processing techniques as and when they are important. So before we go and do dimensional reduction, so in this chapter we wanted to do dimensional reduction, right, which is a form of data modeling. So before we go and do dimensional reduction, we have to pre-process that data so that it's in a form that is much easier for the dimensional reduction algorithms to use it. Okay, so one such operation is called column normalization. So let me explain you what column normalization is. So you obtain your data, you pre-process your data before you go and do data modeling, so that your data is in a nice format. Your data is neatly formatted in such a way, or neatly processed in such a way that the data modeling algorithms can perform good. Okay, one such operation is called column normalization. Let me explain what column normalization is. Okay, I hope I draw the matrix more straight lines this time. Okay, I have my features as columns f1, f2, f3, so on, feature j, so on and so forth. Let's assume I have d features, and I have 1, 2, 3, so on and so forth, n data points. Okay, n cross d. So I'll just forget my y right now, just for simplicity, or let's write it. What's there to lose? Okay, and my ith data point is my xi transpose is written here. Xi transpose is a row vector, right? My yi corresponding is here. My y is basically a n cross 1 column vector. We just saw this, right, a while ago. So what I'll do is column normalization basically does this. Let me explain what it is, and then I'll explain why it is important. I'll also give you some geometric intuition. First, let's understand what it is. Okay, then I'll quickly explain why is it important. Okay, first let's say what is. Let's try to answer the question. What is column normalization? What it means is you take each column. This is a column of data, right? Each column corresponds to a feature. These features are like your sepal lengths, petal lengths, etc. in the iris dataset. Just to refresh your memory on what features are. So you take all the values corresponding to these features. Okay, you take all these values. Let's assume I have values a1, a2, a3, so on and so forth, ai corresponding to the ith data point, and an. So let's assume this is my feature j. Okay, I'm just putting a different value here instead of x1 because x1 corresponds to a data point, right? So take a column. What I'll do is I'll transform all the points in this column as follows. Okay, so And first I process first column, then I process second column. So this is called column normalization, right? Column normalization. So we don't touch yi right now. We don't touch yi at all. We only process these d columns or d features in X, right? And we process each column separately, but we process all the columns. Okay, let's see. I'll show you what we have to do for one column of data. The same thing is done for all columns of data here. Okay, so now I have A1, A2, so on, so forth, AN, okay, as n values of feature J. Okay, right? Because I have n data points, every data point has a value corresponding to the feature. In our case, let's assume, in our case, if you recall, we had 150 flowers. And if I was using, let's say, petal length, I would get petal length for all the 150 flowers, right? Now, I have these values, right? So first I'll process them. Let's assume there is another column, which is B1, B2, so on, so forth, BI, so on, so forth, BI. Then I'll process all Bs. Similarly, Cs, so on, so forth. Okay. So let's see what I do here. What I would do here is, so let's take the maximum value of AI. So the maximum value of each AI. So the general term, I'll call it as AI. Okay, let's call it as max of AI is nothing but the maximum value. Okay, let's give it a name. Let's give it A max. Okay, let's call it A max. Let me just erase this. Okay, A max is the maximum value amongst all of them. Let me call min AI as A min. So A min is the smallest value, which means A max is greater than equal to all AI, and this is less than equal to all AI, with I going from 1 to n. Right? I can range between 1 to n because I have n data points here. Right? This is the definition of A max. So this is the definition of A max and A min. Now let me transform this data. So I'm given A1, A2, A3. I've taken a column of data, right? This is one column of data. I'll transform it as follows. Let me define AI dash. Okay, so I'm given A1, A2, A3, right? I want to create A1 dash, A2 dash, A3 dash, A4 dash, so on so forth, AI dash, so on so forth, AN dash. So from this, I want to create a new data vector. Okay, and how do I create any of these AI dashes? My AI dash is nothing but my AI minus A min by A max minus A min. Now let's see why are we doing this. So before we go, so let's see what happens if you do this. Okay, by doing this, I can guarantee that AI dash, right? AI dash, okay, will lie between 0 and 1. By doing this transformation, see, these numbers could be anything. Your petal lengths could be 1.2, 1.3, 1.4, 1.9, 1.7, any number, doesn't matter to me. It could be any real number. As long as the real numbers are integers, I can transform them by applying this formula such that my A dashes lie between 0 and 1. You can easily see this with the formula, right? Because if I put the minimum AI here, this value becomes 0. Think about it. If I put A min here, so if I used A min, what happens? What happens to A min? It becomes A min minus A min by A max by A min, which is 0. What happens if I transform A max? This is A min dash, right? My A max dash is nothing but A max minus A min. See here, instead of AI, I'm just putting A max. Here, instead of AI, I'm just putting A min, right? A max minus A min. This value is 1. So for the minimum value corresponding to your AI, you're going to get 0. For the maximum value, you're going to get 1. For all other values of AI, you're going to get a number between 0 and 1, right? So now what you're doing here is, given any vector, given any feature vector containing values of A1, A2, AI, AD, you're transforming it into AI dash, sorry, A1 dash, A2 dash, so on, AI dash, so on so forth, AD dash, such that each AI dash belongs to 0, 1. This could, here AIs could belong to any R, any real value, doesn't matter. You're transforming it. So this is your, through column transformation, sorry, through column normalization, you're transforming it into this, right? This part is clear. So what part is clear, right? What are we doing? We now know. Okay, we are now squishing all the values. It could be any real value. We are now compressing it into 0, 1. So that part is clear. So the what part is clear. Now let's understand why are we doing this? Why do column normalization? So for example, let's look at this problem. Suppose I'm collecting heights and weights as two features. Let's just say, suppose my first feature is height, my second feature is weight. Okay. Now, in which scale am I collecting my heights? I could say I'm collecting centimeters, 162 centimeters, 172 centimeters. Okay, let's assume all of my heights are collected in centimeters. All of my heights are collected in kilograms. Okay, so these are heights and weights of each student. So each row corresponds to a student. This is student 1, student 2, so on and so forth, student n. Right? And this is your feature 1, this is your feature 2. Now let's assume your weights are in kilograms. Let's say 56 kilograms, 72 kilograms. Okay, somebody who is, let's say 182 centimeters is 84 kilograms. Somebody who is 150 centimeters is, let's say 58 kilograms, so on and so forth. Right? And these could be any values, right? There is no bound to it. So think about it. If I put each of them as a data point, one of them is in centimeters, one of them is in kilograms, right? So what if somebody collected this data instead of kilograms in pounds? This would roughly double. What if instead of people collecting data in centimeters, they collected in feet or in meters, right? Because real world variables can have many ways of collecting data. So we are saying that, okay, whatever way the data is collected, I want all these values. So from here, I'm going to a space through column normalization. Okay, I'm creating my feature 1 dash, which is height dash, and my feature 2 dash, which is weight dash, in such a way that all these values for each student, student 1, student 2, student 3, so on and so forth, all these values lie between 0 and 1. Similarly, all these values also lie between 0 and 1. Now, I don't care whether they were collected in centimeters or meters or feet, or whether this was in kilograms or pounds. I don't care. Okay, by doing this normalization, I'm getting both my features into one standard format where all the values will lie between 0 and 1. So this is one type of data standardization, or it's actually called data normalization. Not standardization has a different meaning in data science. We'll come to standardization a little later. This is one form of transforming your data such that this is scale independent now. So both of them are in the same range. So the maximum height person will have a value of 1 here. The maximum weight person also will have a weight of 1. Now we'll see why this is more important later on. But for now, just trust me, this is important. Okay, you're getting rid of, so by doing column normalization, you're getting rid of scale and putting everything in the same scale. You're putting all your features in the same scale, right? So scale actually can create problems. When we learn about regression and when we learn about classification techniques, we'll understand why this is why having your variables in different scales could be dangerous. So by putting everything in the same scale of the values will lie between 0 and 1, life becomes much more easy. There is one catch here, which is okay, we'll come to the catch in a while, but most important, we understood why, right? Let's understand the geometric intuition for it. Now let's stick to our heights and weights example, right? So imagine my initial data, my F1 is heights, my F2 is weights. I can represent each person as a data point in this. Let's assume first person is here, the second person. I'll represent each person with a cross or with a small circle. Okay. So let's assume all my people are here. Okay. Of course, as you would know, as heights increase, weights also will increase. We know that for most humans, of course. Okay. So here, okay, this could be for this point, this could be, let's say, 170 centimeters. Okay. And the corresponding weight could be, okay, 65 kilos. Now, by doing transformation, by doing our column normalization, I'm transforming this data as follows. My F1 dash is now my height dash. My F2 dash is my weight dash. What am I doing here? I've transformed each of these points, x-axis and y-axis, to lie between 0 and 1. So literally what I'm doing here is I'm creating a bounding box. So let's assume this is 0 and this is 1 and this is 1. I'll bring all these points within this region. I'm basically literally bringing all of these points. Basically, I'm taking this data, I'm squishing this data without spoiling the relationship between the data points. I'm squishing all of this data and bringing it into a square. This is called a unit square. So this is called a unit square because it's a square of side 1 on this side, size 1. So this is 1, right? And this is 1. So this is called a unit square. So this is 2-dimensional, right? In high dimensional space, what happens? Suppose if I have d dimensions, linear algebra will help us do all of our stuff, right? All of our stuff of interpolating things which we learn in 2D to high dimensions. Suppose if I have high dimensional space, okay, of course I can't draw the dimensionality here. Let's assume I have a bunch of points like this. What it's doing here is it's bringing all this data. Okay, it's bringing, okay, I think I should not draw it. Okay, suppose if this was 3-dimensional data, right? If this was F1, F2, and F3. It'll bring all of this data. If there were 3 features, not height and weight, but let's assume there are 3 features. Let's say you had height, weight, and blood cholesterol or cholesterol. Okay, three measurements. Of course, cholesterol is measured in a different scale. I don't know much of medicine, so I don't know in what metric or in what scale is cholesterol measured. But I don't care, because if I do column normalization, and if I create my new features F1 dash, F2 dash, F3 dash, all of this data will lie in a unit cube, right? Everything here, this is size 1, this is of length 1, and this is of length 1. So literally what column normalization does is it takes your data from n-dimensional space, okay, anywhere in n-dimensional space. Your data could lie anywhere in n-dimensional space. So column normalization will take the data and put all of the data in the unit hypercube, okay, in the same n-dimensional space. So it's basically compressing, or it's actually squishing. It's literally squishing all of this data into a unit cube or a unit cuboid. We'll see why this is useful. Please bear with me. So at least one thing that you understand is we are getting rid of scales, right? We are getting rid of whether the data is in centimeters, meters, feet, for heights, whether it's in kilos or lbs. We're getting rid of these scales, right? And getting everything into the same format. This is useful. We will see later. Trust me. We will see why this is useful when we learn a lot of machine learning. And this data normalization or column normalization is an extremely important task that we'll perform over and over and over again through all of our modeling. Okay. So we also understood the geometric interpretation of data normalization. In the next video, we'll see what is data standardization, which is a similar operation, but slightly different.